14, ball membrane.
Question 14. Yes, we are set.
Thank you.
Okay. Question 14 it is. Okay, please write down the name of your representative of your team on the board. start whenever you are ready.
Honorable jurors and fellow competitors, I am Chen Nankai from Jingchen High School, Mark Chaocha. And today, I'll be reporting problem 14, ball-on membrane. So this is a problem statement. When dropping a metal ball on a rubber membrane stretched over a plastic cup, a sound can be heard. Explain the origin of the sound and explore how its characteristics depend on relevant parameters. So the main focus of this problem is first, how did the sound get produced? And second, how different parameters affect the sound characteristics. So this is my outline. First, I will start off with the observation, and I'll move on to the theory, experimentation, and finally, the conclusion. So this is the observation video. We draw a metal ball on a rubber membrane, which is made from a balloon, and we could hear the sound characteristics, and we use a microphone and volume sensor to get the sound characteristics. So these are some available parameters. Firstly, the metal ball, which we have 3 different sizes, and for tension of the membrane, we also have 3 by alternating different screws, which I'll explain later. And third is the drop height of the ball. And for some sound characteristics, we will test the sound amplitude, and we use fast-forward transform, which transfer the data from time domain to frequency domain, and we could get the peak sound frequency. And third is the collision frequency of our sound. So then I'll move on to the theory. So in our observation, and we can see in this graph that our membrane has a symmetric elasticity around the center. So we can see that the membrane has a series of strings, and we could like the K1, K2, and K3, and we can just and we assume that it has a spring constant of K prime in the center. So how we define the spring constant is by adjusting different turns of screws with our balloon holder over here, which I will also explain later. And we control the same displacements, and we use the electronic spring balance to calculate the force over here, and we could get different spring constants. So this also, and then move on to the theory of a membrane. So if we consider the vibration of the membrane from center to the border as a standing wave, and all the way around all the way around the membrane. So first we have to, and we can use the standing wave formula to calculate its frequency. So first we have to find the the relationship of the linear and the areal density of our membrane. And then we can apply the standing wave formula. And here the force, we use the elasticity force, and we could get how fast the frequency, the membrane will vibrate. And then I'll move on to the energy analysis. So first we assume that our metal ball is dropped from a height h, and it will rebound to the height h prime over here. So the potential energy will transfer to the elasticity of potential energy. And so we can rearrange the equations, and we'll get the deformation of the membrane is this equation. And here the deformation x will cause a pressure variation in the system, and it will cause the sound. And so here I will explain the sound source. So if we first assume the small pressure acoustic pressure variation, P in the background pressure of P naught, and the pressure variation here is caused by the deformation of the membrane. So here for the compressible fluid flow, it will satisfy 2 equations. First, it is the Euler's equation, and second is the continuity equation. And the rho here is the total density, the U is the velocity field, and the P is here is the pressure variation caused by the deformation of the membrane. And if we consider as an isentropic process, and this extension, so the density and the pressure and the velocity field will be written like this, and we insert it into our 2 equations. And then we want to find how the pressure will affect the system. So we use Taylor's expansion to linearize our density here in terms of the pressure. So we could get this term. And by inserting the Euler's equation into the continuity equation, and we could get the sound wave equilibrium in the median. And if we consider the damping effect in our environment, we just add a damping term into our sound wave equation. So here I will move on to my experiment part of this problem. So now first let's look at the problem. So we have a phone in the background to make sure that everything is the measured sound is as accurate as possible. And we use a microphone to get the characteristics of the sound, and a sound volume sensor to get the amplitude of the sound. And we 3D printed a balloon holder with screws, so we can alternate different turns of screws to get different tension of the balloon membrane. And we use an electromagnet to release our metal ball, and the balloon is for the membrane, and I'll explain later. And the plastic cup we use has a radius of 10 centimeters. And here I'll talk about my metal ball sizes. So here are the 3 sizes of a metal ball. So now I'll talk about how I construct my membrane. So first I cut up a huge balloon like this, and we fasten by the balloon holder using screws. And we twist the screws like 3 times or 4 times or 5 times to get the tension of our membrane. And in this experiment, we find it very important to get the tension, to get the platform as flat as possible, to make sure that it has same tension around its radius, and we could get a more accurate experiment result this way. So this is my theoretical prediction that I mentioned in my theory part. Then I'll move on to the first experiment, which is we change the drop height of our metal balls. So this is when we drop from 5 centimeters. We drop from 5 centimeters and 11 centimeters and 15 centimeters, and this is the sound intensity with the time results. And now let's look closer at the graph. We can see when we drop at 15 centimeters, it has a higher initial sound intensity, and it will have a damping effect throughout the time. Now I move on to collision frequency. So the blue line is when we drop from 15 centimeters, and the red is from 13 centimeters. And we can see that because the higher we drop the ball, the higher it has initial potential energy. So the collision frequency will be lower. And then I use the fast-forward transform to get the peak frequency of our sound. And we can find that no matter we change the height, it will always has the same peak frequency of 257.8 Hertz. So my discussion first is the amplitude. So why the higher drop of the ball will have a bigger initial sound amplitude? It's because the higher we drop the sound, the bigger the deformation of the membrane will be, and it will cause a higher pressure variation in your system, so it has a higher sound intensity. And for the collision frequency, because the higher we drop the ball, it has a higher initial potential energy. And we also observe in our fast-forward transform that the peak frequency will remain the same. And for the second experiment, we use a different size of the ball. And this is the 3 different sizes of ball when we drop at 11 centimeters. And this is the result when we drop at 15 centimeters. So from every experiment, we can see that the larger ball has the highest initial sound intensity, and the second is the medium ball, and the smaller is the small ball. And we also use the fast-forward transform to get the peak frequency in our sound, and we also observe that they have the same frequency of 257.8 Hertz. So I'll explain why the bigger ball sizes will have a bigger sound amplitude, and this is the same as my first experiment, is that the bigger deformation of the metal ball will cause bigger pressure variation in our system. And since the tension of the membrane remains the same, so they will have the same peak frequency. And so for the third experiment, I'll experiment with different tension of our membrane. So this is the third experiment, which I change different tension of our membrane. So a big reminder is that we change different turns of screw to get the different tension of our membrane. So this is the fast-forward transform when we use 3 turns of our balloon. And it has a peak frequency of 257.8 Hertz. for 4 turns, it has a higher peak frequency of 275.3 Hertz. And for 5 turns, it has the highest peak frequency of 339.8 Hertz. So for discussion, why the tension will cause, because the tension got bigger, so the vibrating of our membrane will be bigger. So the air will have will have a higher frequency, so we could observe a higher pitch. But the frequency over here is the vibrating of the membrane. It is not the frequency that we observe the sound, but we could find some relationship using this equation. And now I'll move on to the conclusion of this problem. So the first and second is our theoretical conclusion. So the problem statement asks us to explore the origin of this sound, and we think that we found reason, the source of the sound. We think it is the pressure variation caused by a nanoball, and we did the experiment with experiencing different drop height and different sizes of the ball. And the experiment result shows that the bigger the deformation of membrane, it will have a higher volume. And to explore more sound characteristics, we changed different tension of the membrane to get a different pitch. And from the theory, we can see that the frequency will be unchanged, will be proportional to our spring constant, which is the tension of our membrane. And with the higher vibrating of the membrane, we will also observe a higher pitch of the sound. And these are my references. This is the end of my report. Thank you.
Okay. Opponent, please. Your question.
Honorable judges and worthy reporter, I have some questions to discuss about. So
Okay.
first, according to the topic, we have to discuss where is the origin. So where do you think is the origin? The cup, the air around the cup, or the cup?
We think
Or the membrane?
We think it is the deformation of the caused the pressure difference in the fluid. So the upper air and the lower air of our plastic cup.
So which part do you think that caused the sound? The upper air or the air downwards?
So I think both will cause, but the lower part of the air will have a higher.
I see. So in your experiment, do you ensure that your membrane, the tension on your membrane is even? Because we believe that might influence the result.
Yeah, for the experiment, we change balloons very frequently, and so we could make sure that the tension of the membrane is even.
I'm asking, do you ensure the tension on the overall membrane is the same?
Yes.
Okay, thank you. Then how about the experiment with the larger bowl? Do larger bowl has larger contacted area on the membrane?
Yes.
So do you think that will influence the result?
Yes, it will influence the sound. It will influence the sound intensity. But it will not change the frequency of the sound.
Did you take it into consideration?
You mean the larger ball?
A larger bowl has bigger contacted area.
Yeah.
Thank you.
Okay.
So do you think it's the resonance that causes the sound? Do you think that have a place in it?
Yes, I do think so.
So do you calculate the frequency of the resonance?
I didn't calculate the resonance.
Do you think that's standing wave inside the cup?
It is part of the reason that causes the sound.
Do you think the air column, the different membrane, and different materials will influence?
Okay, time's up.
Okay, I guess I think.
Thank you. Okay, honorable judges and reporters, and I'm the opponent from Team Detonation, and now I'll do some explanation and do some remarks on the reporter team. So first, the topic of the ball on the membrane is about discovering the origin of the sound, and second, to find how the different parameters will influence the characteristic of the sound. And for me, we believe that the characteristics should include the frequency and the amplitude. So moving on to how the reporters construct their presentation, and this is the sequence of their presentation. So first, it's about their theory and phenomenon. It gives us a great observation video, and they define spring constant. Additionally, they use standing wave to explain the origin of the sound and also the vibration of the air around the cup. For the experiment, they use the different parameters and detect the sound with their microphone and a series of setup, and discover the characteristics of some frequency, certain frequency, which is the first lowest frequency of the sound, and the amplitude of the sound. And for their conclusion, the pressure from the vibration caused the sound, and the vibration is from the vibration of the air molecules. And second, tension caused higher pitch. And third, they conclude that the larger the ball and the height is, the volume increases. And they explain this with the transformation of energy. And now is their theory and experiment. For the theory, they start with energy analyses, and they do experiments with their membrane. And for their sound source, they use Euler equation and continuity equation, and also Taylor expansion to explore the sound. And also, they use acoustic analysis and standing wave formula to calculate. And for the parameters, they use metal ball radius, and second, tension of the membrane, and the drop height. These are the reporter's conclusion. So first, pressure from a vibration caused sound, and second, tension caused higher pitch. And third, as the size of the ball and the release height increases, the volume increases. Okay, here's the strengths and weaknesses we consider for the reporter. So first, for the strengths, they use energy to discuss the motion, and second, Euler equation and continuity equation to explain the pressure. And third, the good way of controlling the initial condition of the ball. And the fourth, they talks about the characteristic of the sound intensity. And they use intensity to explain the sound characteristics. And for the weaknesses, we believe they lack the explanation of how the screws can ensure the tension is even on the membrane. And second, they didn't talk about background noise that may influence the result from the spectrum of the sound. And third, they lack the discussion with the other peaks of the frequency. They only talk about the lowest frequency, which we believe may be the fundamental frequency. And the fourth, they didn't have clear definition of the sizes of the ball. They just use small, medium, and large. That is the part that we believe can improve. And the last one, they lack discussion with the air column below, which is part of the origin of the sound. And here's the discussion we are doing today for the experiments, including different parameters, the origin of the sound, and the influence of bigger contacted area, and also the setup of experiment and calculation. For the theory, including the sound origin and resonance. Now I'll start my discussion. Please. So in the previous discussion, you said that you believe the sound is caused by resonance.
Yes.
So can I use the blackboard? Can I?
Sure.
Thank you. So can you calculate the fundamental frequency that caused by the resonance?
You mean caused by the pressure variation of the fluid?
Yeah.
And you mean can I calculate the frequency of the sound using treatment of the sound? You mean theoretically?
I'm asking you so that if you can calculate the frequency, the lowest frequency you detect in your experiment, which caused by the resonance, you said.
Okay, so you think that the main frequency, which is the main frequency we observe in our experiment, like in my fast forward transform data. So the biggest peak, we think it is the main frequency.
So do you think the main frequency is the fundamental frequency?
Yeah. So the fundamental frequency is defined like the n here is 1, right?
That's true.
So we think that this is the main fundamental frequency that we can see in the fast forward transform graphs. So I just do it. So like we think that the pitch here, so the main pitch from the fast forward transform data is the fundamental frequency.
Yeah. And I would like to continue on this question. Can you please turn to the page of your experimental setup? So can you tell me how high is your plastic cup?
So the plastic cup here is
The height. Yeah.
height is 5 centimeters. Okay, so the height of the plastic cup is 5 centimeters.
Maybe it's 10 centimeters there.
You mean the height of the plastic cup?
Yeah.
Yeah, 5 centimeters.
And the L here refers to 0.1 meter. And the velocity of air, can you tell me the velocity of air during the condition?
We think it is maybe like 200 and like 340 maybe?
Yeah, you agree.
340.
So the velocity here is 340, and we can do the calculation here. So we get the frequency equals to 340 over 0.4. So what's the frequency here? It's about 850. So can you show the spectrum of your sound
Okay.
that you detect?
No.
So it seems strange for me because on your graph, the fundamental frequency you said is about 275. However, after a calculation, it's 850. So do you still consider it's the resonance that caused the sound?
Okay. So I want to further explain that we don't think that it is the resonance that will cause the sound.
Okay. So what do you think is the origin of the sound according to the topic today?
Yes, we think it is caused by the pressure variation in our air.
Yep. So do you think that there will be a difference if we do not have a plastic cup under the membrane? Because in your statement, the plastic cup will not deal with the frequency because it's not resonance, it's just the vibration of the air molecules around the cup.
Okay. So you mean that if we don't put, so in the experiment we observed that if we didn't put a plastic cup under here, that the volume of sound would be extremely hard to detect.
Yep, and I am interested in the frequency of the sound.
Okay, so the frequency of the sound, we do not think that is mainly caused by resonance, but it may be caused by other factors. That we could observe the frequency, because we know that the frequency like do re mi fa sol la si do is close. It is like 275.3 hertz. It is around that level. So we do not think that there is a deviation here in my experiment graph. But here we do not know that the effects of the plastic cup under here.
So, what I'm interested in is what do you mean by other factors that causes the sound of the membrane? Because this is what we're discussing about today.
Okay, so in my background knowledge, this is the equation for open or an open, like an open here, and it is
A block under.
oh, it is block under. So the
One
force
side
for-
open and one side block.
Okay, so in my experiment, we closed we closed our plastic cup. So I think the frequency over here should be like 2 or 2.
What do you mean by?
No, so this, I mean, so I have to show you how the plastic cup. So here the plastic cup, we have a little hole under here, so we can make sure that the pressure here is the same. Okay, so
So you mean that the air column of the plastic cup does not matter in this experiment?
so from my experiment, we do not, because it does not match the result with the resonant frequency, so we do not think that the resonant is the main reason that will the frequency of the sound.
I see. So can you please turn to the page of your experiment setup? I want to know, how do you control the ball falling? So what's your setup for controlling the ball when it falls and when it does not?
Okay, so we control the dropping of the ball with electromagnet, so we can ensure that it has the same drop height.
I see, I see. So you mean that, what is the reason for using the magnet? It's because of energy or the force or what?
Because if we release by the hand, we think that it will cause some initial spin, or it cannot hit the center of our membrane, because in our theoretical theory, we consider that it will hit the center. So,
Okay, so your experiment, you throw the ball on the center. So what do you think if we do not throw the ball onto the center, we throw it onto the side, what the sound may be?
okay, so this is a very interesting question, because
I believe it too.
yeah, the membrane has the same tension gradient across the radial direction. So like the tension would be the lowest here, so the tension of the, sorry. So here's the displacement and here's the tension. I believe that it would look something like this. So it would be bigger around at the border of the plastic cup. And can I ask you a question again?
Question?
Oh, wait, so, sorry.
Okay, okay. Okay.
Hold on for a second. So, because the tension here is bigger, so it will cause if our ball is over here and the deformations, because the tension here is bigger due to my graph over here, like this. So tension here is bigger and tension here is smaller, so it would fall like, it would here in this direction, and it will not have the big sound as we could observe in the center.
I agree with you. However, I'm interested in the frequency too. So what will it be if we do not throw the ball into the center? Will the frequency be higher or lower or not changing?
Oh, okay. Because we consider a standing wave from the center to the border up here. So if we contact the ball over here, so there, I believe that the standing wave would be like, will be very diverse. But we think that we could use fast forward transform to get like, which is the peak frequency, and we could observe the frequency using fast forward transform this way.
Yeah, I'm really interested in the graph you draw here. So are you mean that the tension will go to infinity in the condition?
No. So here is the border, like maybe, so it is like 10 centimeters. So.
Okay, I see. So here's also another discussion during the previous discussion stand, and you said that the air column and different membrane and different materials of the cup will influence the outcome. So I'd like to first start with the air column. So what do you think the result will be for different air column of the plastic cup? Because I do not see it in your experiment.
Okay, so we control drew the same air column in our experiment. So I think that with a bigger column, so the pressure variation, we think it is mainly caused by the downward air.
Downward air, but you said the upward and the downward.
Yeah, the downward air, we think that will impact most of the sound because
Why most of the
yeah,
sound?
because it will like bounce in the middle here and it will echo. So it's like the mechanism of a drum.
So are you changing your statements to that the curve will influence the characteristic of the sound?
Sorry, what?
Because previously you said that the curve does not have a great influence for the characteristics of the sound which we made from the ball falling. However, you said that the curve have influences here. So what's your final statement here?
So we do not think that the frequency or the effect, like the frequency will not depend on the cylindrical plastic cup over here, but we do think that the air could be like echoing inside the plastic cup, so it would have a bigger sound.
Okay,
Yeah.
so you think the frequency will not change?
Yeah, frequency will not change due to the same membrane.
Okay, so you think that it doesn't change, so do you have experiments to prove it?
We don't have the experiment for different colors, but if we remain the same membrane with different heights, we could have we observe the same peak frequency.
So can you please turn your page to page 27? So here's a question that I want to ask is that you said that you do experiments and observe the frequency, which is the lowest. So what do you think is the meaning of the lowest? Do you think there will be other frequency after the lowest frequency?
You mean the fundamental frequency you mentioned?
Yeah. Do you think there will be some overtone frequency after the fundamental one?
Yeah, we do think so. So in the FFT graph, we could observe that it has a highest and it will have a second.
I understand. So why don't you analyze the frequency after the fundamental frequency? Because I believe that might be influenced with different
tension.
with different characteristics in your experiment, different condition in your experiment.
Yeah, so we think that the fundamental frequency is like the peak frequency, and it will be the main. It will consist mainly in our experiment, mainly in our sound. So we only observe the peak
Okay,
frequency.
time's up.
Thank you.
Tunnel?
Now is our conclusion for the previous discussion. So first we talked about the experimental setup, and they said use the magnet to make sure it's fall onto the center. However, they did not do experiments which the ball falls onto other sides. I believe that might cause difference to the results. And also, they said that it's the resonance in the beginning. However, after the calculation, they find out it's not. And they also used the standing wave again in their vibration of the membrane. And also, for the consideration of air column, they stated that that will increase the sound. However, the frequency will be the same. We believe they might need more experiments on this and discover the reason why they think it's not changing.
Okay.
Thanks for listening.
Reviewer? No question?
First, do you think the origin of the sound comes from the resonance of air particles?
Yes, I do think so.
And for the opponent?
I believe the origin of the sound comes from the vibration of the membrane. And the vibration of the membrane causes the vibration of the air molecules.
Okay, thank you. And for the reporter, please turn to page 35. So do you think that what causes a second peak?
The different resonances of the sound.
Do you think it's multiplication frequency? Since the second peak appears with about the 540
Okay.
Hz, and do you agree with that?
We believe the second peak is because of the different vibration mode on the membrane.
You mean multiplication frequency?
I mean, there will be a certain frequency of the vibration, the second vibration mode, which is caused by the.
Okay, thank you.
Thank you.
Will the diameter of the manifold affect the wave speed of the sound for the opponent?
Can you rephrase your
Will
question?
the diameter of manifold affect the wave speed?
I believe it's the mass that influences, and absolutely, when we have bigger radius, it causes bigger mass. So
Okay, thank
we
you.
think so.
And do you think that the deformation will cause a different wave speed in your experiment?
We think that you mean the wave speed in the sound or on the membrane.
Of the sound?
We think the temperature will be
I
causing
mean,
the
deformation.
deformation of membrane. We don't think so.
Then how about the opponent? Do you think the deformation will cause a different wave speed?
We don't think so because the wave speed, the voice speed is constant. And for the previous question, I got a wrong question for my understanding. What I mean is that the wave speed will not change.
Okay, thank you. And what is the relation between frequency and intensity?
We don't see a relationship between intensity and the frequency of the sound.
And can you predict how will the wave act on the membrane?
We cannot predict.
Okay. And do you think the different landing position on the membrane is an important parameter to consider?
Yes, we do think so. It will affect the deformation of membrane. It will cause the intensity of the sound to alter, but the frequency of the sound, we think it will remain the same.
Okay, thank you. And do you think the shape of membrane, for example, a square membrane or a circular membrane that you're doing in your experiment will affect the result?
Yes, I do think so.
And how about the opponent?
Yes, we do think so because we believe the origin of the sound is the vibration of the membrane. So if we have different shape of the membrane, for example.
Okay, time's up.
Thank you.
The viewer, you have 2 minutes to prepare.
Honorable juries, fellow competitors, this is a reviewer from Team Excel here, reviewing problem number 14, ball on membrane. When dropping a metal ball on a rubber membrane stretched over a plastic cup, a sound can be heard. Explain the origin of this sound and explore how its characteristics depend on relevant parameters. And the main focus would be the origin of this sound and how the different parameters such as landing position, radius of plastic cup affect the characteristics of the sound. And for the reporter's outline, for the phenomenon part, he had an observation about the rebounding of metal and theory in regards to energy analysis, acoustic angles, Euler's equation, and continuity equation. And he did experimental parameters including 3 sizes of ball, tension of membrane, releasing height. These are the pros and cons that I think the reporter had. First of all, he has a clear observation of phenomenon. However, in his theory part, there's a too idealized experiment about the deformation, which he did not have a explanation about the deviation. And he did not have a theory line for his data. In his experiment part, he has a proper method to control the spring constant. However, the reviewer believes that the landing position, height, and size of plastic cup should be also important parameter to be considered. Opponent mainly discussed about the origin of the sound and the influence of contact areas. For the pros and cons of opponent, first, deep understanding on the reporter's theory. However, there's too much irrelevant discussion on theory and the setup, which makes the lack of discussion of the experiment. For the first discussion about the origin of the sound, the reviewer disagrees with the reporter. The origin of the sound should come from the resonance that comes from the vibration of membrane and causes the resonance of air particles. For the second part of discussion about deformation, the reviewer also disagrees with the reporter. Although you can avoid elastic fatigue by the changing frequency of membrane, however, the deformation when the ball collides to the membrane still exists and will cause different wave speed because immediately tension is different. For the next discussion about frequency of the sound, I agree with the reporter and believe that the parameters such as tension of membrane and radius of the cup is the main reason to affect the wave speed. These are the points missed. First, the origin of the sound is not well discussed. The reviewer believes that it comes from the vibration of membrane and causes the resonance of air particles, and because we're measuring the sound, so it causes a multiplication frequency. And because the deformation, there are multiple contact points, which causes the harmonic of the sound. And he did not discuss about the deformation of membrane. And in his experiment, he did not consider the areal density, which would affect the wave speed a lot. And he also didn't measure the magnitude of the areal density. And there's a lack of important parameters such as landing position, shape of membrane, radius of the cup. And they did not discuss well about the energy transformation of the ball. For the plane shape part, I believe that the different kind of waves acts on different kinds of membranes, such as square and circular. It might cause different waves, such as sine wave, or waves that conform to basal function. And because when you are changing the shape of the wave, the boundary condition could be changed by the edge of the cup and the shape of the membrane. So it should have a different kind of wave speed and wave dynamic. And they did not discuss about the relation between frequency and sound intensity. Well, thank you.
Okay. The reporter, your concluding remark.
So here is my concluding remarks. So firstly, we observe that in the graph, like the center, the tension will be at the same distance from the center because we can control our experiment with the balloon holders. So for the origin of the sound, through the discussion with opponent and reviewer, in addition to the origin, we think it's from the pressure variation. We also think that it is because of the resonance of air molecules that will cause the different characteristics of the sound. And for the frequency, we think that depends on the tension. And if we did not drop directly at the center, we think that because the tension not in the center will have a higher tension, so it will cause a smaller deformation. So it means that it has a smaller sound. And for the frequency, by not dropping in the center, the reporter think that it will cause different vibration mode on the membrane, but because we did not consider this in our experiment, so we just we could assume that it has a higher tension, so it will have a higher frequency of the sound. So this is the end of my report, and through a discussion we know more about this problem, and thank you.
Okay. Okay. Any questions from George?
According to the opinion of the opponent, do you think the origin sound from the membrane vibration, okay?
That's right.
If you want to prove it, how do you design your experiment? Answer in brief, thank you.
Yes. So we believe the origin of the sound made by the membrane, and because the vibration of the membrane has a function called basal function, and the vibration of the membrane follows it and has certain frequency. So if the sound that we detected from our microphone fits the certain frequency, the certain ratio between each frequencies, then we can verify that that's from the vibration of the membrane.
I agree with the opponent.
Now please turn to page 35. To prove that the origin of the sound really comes from the vibration of membrane, then causes a resonance of the air particles. The multiplication frequency between the 500 to 1,000, there is a peak that is about in this 540 is the multiplication frequency of the first peak.
Thank you.
Any more questions? Okay, I have a question to all of you. So, do you consider that the material of the cup relevant to the experiment?
Can I answer first?
Sure.
So we believe that because we think that the origin is the membrane, and the cup serves as the area that amplifies the sound. So the different materials of the cup, it takes away the energy faster, which will cause the sound to become lower. However, the frequency will be the same if other conditions remains. We believe this way.
How about you?
It causes the different resonance of the sound, so it will cause difference for the wave speed.
And okay, so I agree with the opponent with the different substances that will absorb different sound energies, and we do think that the frequency will be same due to the causing origin of the sound is the deformation of the membrane. Okay, thank you.
Can I add a point for the question?
Sure.
I think maybe the resonance of the container will amplitude certain frequency of the spectrum. So take this into consideration. Maybe with different materials of the cup, the certain frequency will become the highest, and that might be the natural frequency of the container. That's my opinion. Thank you.
And can I add a point to that answer? So in my experiment and also the calculations, I do not think that the sound resonating in the cup would be the main frequency, but the resonance of the sound, like the reviewer has said, the resonance of the air molecules would be the main of the sound characteristics. That's it. My answer.
Any more questions? No? Okay, so let's prepare the score. B. Okay, so let's show the score for the reporter. 6, 6, 7, 6, and 7. For the opponent, 6, 7, 7, 8, and 6. And for the reviewer, 6, 7, 7, 8, and 6. Okay, thank you. So that concludes today's fight. Thank you very much.